This was tough. 4 minutes, my. IT Integration Bee 2023 Finals Problem Number 3. Central to solving this problem is the integral of the square root of the general quadratic ax squared plus bx plus c. This is where we'll begin. To start, what I'm going to do is I'm going to take the quadratic and complete the square. Ax squared plus bx plus c, rewritten in what we can call completing the square form, or sometimes known as vertex form. Written in terms of the coefficients a, b, and c, we can now rewrite this integral as the integral of the square root of a, parentheses, x plus b over 2a squared plus 4ac minus b squared over 4a squared, all underneath the radical there. We can factor out the square root of a and leave us with the radicand in the integrand, which is a little bit simpler. So then the next thing we'll do is we'll make a substitution. We'll start by letting u equal the binomial x plus b over 2a, and therefore du would be equal to dx. Also, we're going to let t squared be the term 4ac minus b squared over 4a squared, so that t would be equal to the square root of 4a squared minus b squared all over 2a. So now we can write this integral as the square root of a, integral of the square root of u squared plus t squared du. We can then also factor out a t from the square root and rewrite the radicand of the integrand in a simpler way. Next, we're going to make another substitution. We're going to let v equal u over t, so that t dv is equal to du. And then we can rewrite the integral as t squared square root of a, the integral of square root of v squared plus 1 dv. Now the next step is a trigonometric substitution by letting v equal the tangent of theta. That would make dv equal to the secant squared theta d theta. And with this substitution, we get the integral to be t squared, square root of a, integral of the square root of tan squared theta plus 1 secant squared theta d theta. And we can now make another trigonometric substitution. Tan squared plus 1 is equal to secant squared, and so we can get rid of that radical with the trigonometric substitution, leaving us with the integral of secant cubed theta d theta to solve. This is where integration by parts will come in. Now I'm going to use the variables w and z, so we'll get w equal to the secant of theta and dz equal to the secant squared of theta for our integrand here. And differentiating, dw would be equal to secant theta tan theta d theta. Z would work out to be tan theta. And the integration by parts formula is the integral of w dz will be equal to wz minus the integral of z dw. Substituting in our values here, we get the integral of the secant cubed theta d theta is equal to secant theta tan theta minus the integral of tan squared theta secant theta d theta. Now we can make another trigonometric substitution again here. Tan squared theta is equal to secant squared theta minus 1. So now this becomes secant theta tan theta minus the integral of secant cubed theta d theta plus the integral of secant theta d theta. And you'll notice that two of the integrals on both sides of the equation match. So we can bring them together, collect like terms, and get 2 times the integral of secant cubed theta d theta is equal to secant theta tan theta plus integral of secant theta d theta. And bringing a factor of 1/2 to the other side, then 1/2 secant theta tan theta plus the integral of secant, and that's the next integral we'll have to take care of, the integral of secant. So the integral of secant theta d theta is done with a tricky substitution of a fancy form of 1. And we're going to put secant theta plus tan theta over itself, so multiplying by it will be essentially like multiplying by 1. But this substitution is clever. So we'll let lambda be this substitution of secant theta plus tan theta, and with differentiating that, we'll find that something interesting happens here. So simplifying our differential of d lambda, we get secant theta times secant theta plus tan theta d theta, and wouldn't you know, that's in the numerator of our integral. So now this just becomes the integral of d lambda over lambda, which we know is the integral that equals the natural log of the absolute value of lambda, which here is the natural log of the absolute value of secant theta plus tan theta. So now I is equal to t squared square root of a, and substituting in for the secant cubed integral, we get 1/2 secant theta tan theta plus natural log of the sum of secant and tan theta. It's a mouthful to say it every time, so here I'll just shorten it up. So I is equal to this constant, we'll pull the value of 1/2 out of there, secant times tangent plus the log of secant plus tangent. Now all it takes is a little bit of back substitution, and actually we're going to have to work out secant theta and tan theta using a little right triangle trigonometry. So in order to sort of get these values back into things that we can use to substitute in terms of the coefficients a, b, and c from our original problem, we'll remind ourselves that u was equal to x plus b over 2a. And if we multiply both sides of that equation and rearrange some terms, we get u is equal to 2ax plus b all over 2a. Representing it like this will become useful later. Now v was equal to the tangent of theta, which is also equal to u over t by our definition. So we can rewrite that the t is equal to the square root of 4ac minus b squared over 2a. And that, taking the reciprocal of that, will help us in what we need to calculate next. So u times 1 over t will give us v is equal to 2ax plus b over 2a multiplied with 2a over the square root of 4ac minus b squared, which ultimately simplifies to 2ax plus b over the square root of 4ac minus b squared. So these two things will help us now back substitute, and again with a little help from some right triangle trigonometry. So if tangent of theta, and we'll use theta in our triangle here, tangent of theta is equal to 2ax plus b over the radical of 4ac minus b squared. It's the opposite over the adjacent from that angle, so we'll set the triangle up accordingly and solve for the hypotenuse of that triangle using good old Pythagoras. And it works out to be 2 square root of a multiplied by the square root of ax squared plus bx plus c. Very convenient. And the secant, which we know is defined as the hypotenuse over the adjacent, we can collect the terms here and write an expression for the secant of theta. Now that we have two rational expressions here for tangent theta, secant theta, and that shows up very prevalently in our equation, now we can write it in terms of the coefficients a, b, and c. It's going to be a rather complicated expression, but it is like a formula. We can just plug in a, b, and c and get the values that we need. So for the sum of secant plus tan, we get one expression, and for the product of tangent and secant, we get another, all involving some radicals and some constants. But again, that will clean up in a few minutes. And this is all going to pay off when we want to try and solve the integral from the MIT Integration Bee 2023 Finals number 3. So just cleaning this expression up, And rewriting it in the simplest form as we can for now, we get an expression for both the secant plus tan and the secant times the tangent. All right, so we're going to lock that into our toolbox, and we'll now bring all of this together. So writing out what our integral is by using all these substitutions, we're going to get a nice expression, albeit a rather complicated looking one. But this expression will allow us to evaluate this integral by using the limits of integration on the integral, as well as by knowing what a, b, and c are. And that's all going to come together after we develop the final pieces of our tool here. All right, we're almost there, and you're doing a great job sticking with me. We now have the integral of the square root of the general quadratic ax squared plus bx plus c, and we're going to do a specific example for the quadratic x squared plus 1x plus 1. So the coefficients a, b, and c are all equal to 1. So when we do this, we're going to plug into our formula, and we'll get a general expression in terms of x for that particular integral. Now we won't worry about the constant of integration right now because we're going to evaluate this at limits later on. Now we'll call this integral 1, example 1, with the quadratic x squared plus x plus 1. And I'm going to do a quick one here for the quadratic x squared minus x plus 1. So by doing these two integrals, we'll call them I1 and I2. Once we know the formula and the recipe for how these two work, it'll tie everything in together to solve the ultimate integral for our MIT integration bee problem. Alright, and you can see there's a bit of symmetry to the nature of the solutions for both I1 and I2, with just a plus or a minus sign depending on the value of b in that equation. So we have these two mega tools here locked in for those two integrals, and now it's time for the main event. The MIT Integration Bee 2023 Finals Problem number 3. The integral is from negative 1/2 to positive 1/2 of the square root of x squared plus 1 plus the square root of x to the 4th plus x squared plus 1 dx. A formidable integral for sure. Now, we're going to start by trying to simplify the integrand, and the thing that we can notice here is that the entire integrand here is an even function. So by symmetry, we can reduce the limits of integration from negative 1/2 to positive 1/2 and write the integral as 2 times the integral from 0 to 1/2 of that crazy looking radical. Now next, we're going to factor the inner radicand, that x to the 4th plus x squared plus 1. And this will factor into x squared plus x plus 1 and x squared minus x plus 1. Look familiar? Now, in order to find those two factors, here's how you would do it. You assume that this will factor into two general quadratics of the form ax squared plus bx plus c and dx squared plus ex plus f. And then you would multiply out the right-hand side of this so that you would get to collect like terms, and then you can equate both the left and the right-hand sides in terms of their coefficients. And by doing so, you would set yourself up a little system of equations, all in terms of the coefficients. Once you solve those coefficients, you would find that a, b, and c were equal to 1, and d is equal to 1, e is equal to negative 1, and f is equal to positive 1. So there you go. Now that we know how that thing factors, we can rewrite our integral as 2 times from the integral from 0 to 1/2 of the radical square root of x squared plus 1 plus the square root of those two factors now. Now next we're going to do a little clever trick here, and we're going to multiply the entire radicand by a fancy form of 1, namely 2 over 2. So multiplying the first part of that, we'll distribute the 2 over 2 in there. That'll give us 2x squared plus 2 over 2 plus 2 times, and the denominator of that second one I'll absorb into the inner radical, so it'll have to be 4. Now, next we're going to split up 2x squared into x squared plus x squared, and 2 into 1 plus 1 in that first part, fractional part of the radical. And we're going to split the 4 up in that other radical as 2 times 2. Next, we're going to add and subtract x to the numerator of that fractional part of the radical. And now what we can do is we can separate that fractional part as the sum of 2 fractions. And we can look at inside that inner radical as a product of 2 fractions. And so you see here, we get x squared plus x plus 1 over 2 plus x squared minus x plus 1 over 2 as those 2 fractions I was referring to. And so we notice that this radical is of the general form square root of a plus b plus 2 square root of a plus a times b. And that inner part, the a plus b plus 2 radical ab, can be factored into square root of a plus square root of b squared. And so we can pull that thing out of the bigger square root, and our integrand just becomes the square root of x squared plus x plus 1 over 2 plus the radical of x squared minus x plus 1 over 2. So our integral from 2 to 0 to 1 half, from 0 to 1 half of the square root of x squared plus 1 plus the square root of x to the fourth plus x squared plus 1 dx is now 2 times the integral from 0 to 1 half of the first integral there of that fraction, plus the integral from 0 to 1 half of that second fraction in the radical. And now we can, by linearity, split those two integrals and solve them. We can pull out a factor of 1 over square root of 2, so we can simplify the radicands and simplify the integrand in each of those integrals. And now hopefully you can see the tools that we developed earlier and the examples that we created earlier are exactly those two integrals. Now we just have to evaluate those at the limits from 0 to infinity. Sorry, not 0 to infinity, from 0 to 1 half. So we'll call each of those integrals I1 and I2, and we have the limits of integration from 0 to 1 half, and with some careful substitution, these are the values we get for I1 and I2. So now all we have to do is add the values of those two integrals I1 plus I2, and our final integral becomes the square root of 2 over 2, multiplied by the square root of 7 over 2, plus 3/4 natural log of 2 plus rad 7 over rad 3. And that's the final answer to our MIT Integration Bee 2023 Finals Problem number 3. And of course, we should check our solution in Desmos to be absolutely sure that we did everything right. Alright, first we'll enter in our integral from the MIT Integration Bee here. We get a decimal value of approximately 1.45866291429. Now entering in our solution that we found. Looks like it's a match. We did it. That was tough. Hey, thanks for watching. hope you enjoyed it. Stay tuned for the next one. Please hit that like, subscribe, and notification bell for more videos.